Hey guys, all right. So we have arrived at Thursday's video. I know some of you are still kind of letting me know that you're out sick. I did post the actual note packet and calendar on Schoology as well, so people at home could print it out. I'm hanging tough. One of my daughters is pretty much symptom free. The other's kind of coming out of it. You can probably still tell I've still got a little congestion and stuff, but I'm hanging tough, man. I'm back Monday. I'm cleared to come back, assuming nothing drastically changes. So looking forward to it. Okay, so we just did P land. There's P land and then there's mean land, and for the rest of this class, right, we're either going to be talking about proportions or sample means. Yeah, and we just learned everything we needed to about a proportion. We learned that the mean of this p hat is just p, and the standard deviation of p hat is the square root of p times 1 minus p over n. Yeah, and then we talked about the 10% and then normality. Yeah, and we're just going to do the same thing with means, and we're gonna run tests based on proportions and then based on means. What's the difference, you guys? Literally, it comes down to the question that you're asking, right? I think we just talked about, let's go ask a sample of 100 foothillers, hey, have you ever broken a bone before? Well, think about what you're going to get if 25 people tell you they broke a bone. You just figured out that 0.25, or a probability, right, or a proportion, I'm sorry, of people broke their bone, right? If you go out and you ask 100 foothillers what their average GPA is, you're not living in P land anymore. You're living in mean land, right? And so this really just comes down to what type of data are you collecting? Are you collecting a proportion, and then all of these things apply? Or are you collecting information about averages or means? Okay, and everything's the same. This is the benefit, not everything, but it's very similar. We're going to get a mean, we're going to get a standard deviation, and then we're going to be able to check about normality so that we can calculate probabilities of events happening. Okay. All right. So we're going to go out into the foothill land, and we're going to ask people a question. And when you ask 100 people, what their average GPA is, the average of your sample is just the population mean. And the standard deviation is just going to be your population standard deviation divided by the square root of n, as long as the population is 10 times the sample size. So all this stuff is real similar and should be kind of familiar. Again, these are given to you. These equations are given on your formula sheet. So your formula sheet will obviously come in much more handy on all of our assessments and quizzes. You can always use it. Okay. There's this one thing here that it doesn't mention. It's normality. Okay. And I really don't like the way these notes kind of go through this, but I would like to just skip down to the bottom. So when they ask you about normality, what's going to happen at the very beginning is they're going to tell you the population is normally distributed. If they tell you that the population is normally distributed, then the sampling distribution is normally distributed. So it's much easier. Remember in N and P land, the last couple of days you had to check NP greater than or equal to 10 and N times 1 minus P greater than or equal to 10. That's gone. That does not exist over here. All that has to happen over here is they need to tell you something about the population. Okay. All right. So let's check it out. So, example: number of absences last year for students at a large high school has an average of 5.6 days and a standard deviation of 4.1. Okay. Suppose we take a simple random sample of 80 of last year's students and calculate the mean and number of absences for the members of the sample. Okay. So, what do they give us? They tell us the actual population mean. This is population mean. Notation is important. It's mu. Mu is equal to 5.6. They tell us the population standard deviation is sigma. That's equal to 4.1. Okay. But now we're going to take an SRS of 80. Okay. So for A, if you're taking a sample size of 80 students, the mean of that sample size is just equal to the population mean. So it's exactly the same. It's still 5.6. But the variability of your sample distribution will change because you're taking a sample of 80 people. This is a standard deviation if you're just looking at one at a time. But if you're using 80 students, your standard deviation is that population standard deviation over the square root of n. So you have to take that 4.1 and divide it by the square root of 80. And so we hit alpha y equals enter. We got 4.1 over the square root of 80. And we got 0.458. Okay. So we calculated the mean. I think that was A. And then for B, we calculated this standard deviation. Now, what's up with the 10% condition? You have to check, is the population greater than or equal to 10 times the sample? That's our question. So is the population greater than or equal to 10 times 80 equals 800, right? This is a question. And sometimes you guys, they don't tell us, hey, the population is this big. It's talking about the mean number of absences for students at a large high school. So they didn't tell us it's bigger than 800, right? But if they said it's a large high school, so all we can do is assume, therefore, assume assume population greater than or equal to 800. Check, right? They told us it's a large high school. And so you're just, again, this is weird for math people. You're like, whoa, what if it was 750? You're right. Then our assumption would be wrong. What the AP reader cares about is that you're checking conditions. You're aware that you should not use this standard deviation unless you can talk about this independence because you're sampling students without replacement. And if the population's big enough, we don't care when we take out 80 kids from it. It doesn't change the odds of certain things happening. Okay? All right. I think this next example is going to be good. It kind of solidifies the difference between what we did, because this should look kind of familiar, and what we now have with bigger samples. So you've got Mr. Rose, new quality control inspector at a factory, produces axles for a certain model of car. Because the manufacturing process takes several steps, there's some variability in the length of the axles. Specifically, the distribution of axles is normal with a mean of 597, standard deviation of 5.3. So back in chapter 3, we would have said, hey, this is a normal distribution, excuse me, with a mean of 597 and a standard deviation of 5.3. Okay, so let's do A. A has nothing to do with anything we've learned because we're going to select a sample size of 1. Okay, find the probability that the length is less than 595. So find probability that the length of the axle is less than 595. You guys were super good at this. You had a normal distribution, mean of 597, standard deviation of 5.3. We want to know what's the probability it's less than 595. So somewhere right around there. And you'd say, hey, just do normal CDF with a lower of negative 10,000, an upper of 595, a mean of 597, and a standard deviation of 5.3. And this is not new. You guys nailed this, right? This is all old stuff. You go in here and you can hit distribution normal, cumulative from a negative small number up to 595 with a mean of 597 and a standard deviation of 5.3. Okay, and you get 0.35. Okay, so there's a 35% chance that you get an axle length that's less than 595 millimeters. Now, maybe that's a problem, right? Maybe the quality control guy's like, nah, that's not good. If it's less than 595, the wheels aren't going to fit on there. So we got to fix that. Okay? All right. So this is new. This is very new. Now look at what B says. You're going to randomly select 20 axles, right? Find the probability that the average length of all 20 of those axles is less than 595. So you pick one out, the probability is 0.35. Now pick 20. Okay? If they average 597, I'm feeling like it's going to be less likely that the average of all 20 of those is less than 595. And the only way we can do this, you guys, is if we get this fancy drawing with a mean and a standard deviation. But what changes if you have a sample size of 20? The new mean of that sample is the old mean, which is still 597. But the standard deviation of that sample size changes. It's the standard deviation of the population divided by the square root of your sample size. So I have to go take that 5.3 and divide by the square root of 20. And what you're going to see here, you guys, is if you do this, your variability went down to 1.185, right? So the the standard deviation is less because you took 20, right? They're not going to vary as much as 1. It's much less likely if you have an average and you take 20, you're going to get closer to that average. And so that's all that's changed. We have a new mean and a new standard deviation. So we can do our picture, 597, standard deviation 1.185. And we want to know, same question, what's the likelihood that all 20 of those has an average? Now we do the same thing, normal CDF, blah, blah, blah. For sake of upload from my house, I'm going to skip that. We're going to come right in here. We're going to say, look, normal CDF, I'm still starting down there. I'm still going there. My average is still the same, but my standard deviation is now 1.185. And like we thought, 0.05, you're now at a 5% chance that the average of all 20 axles is less than 595 for whatever reason why that matters. Okay, so if that confused you, the benefit of these videos is you can quickly rewind and replay it. All right. Okay. Yeah. So we just kind of talked about normality. So this central limit theorem is all about normality. Why do we care so much about normality? Because I can't do this. I can't type that in. I can't get my answer unless I know that the shape is approximately normal. Okay. Now, look what happened in this question. It said specifically the distribution of axle lengths is normal. So they told us, right, that our overall population is normal. So we were allowed to assume normality. Technically down here, right, is the population greater than or equal to 10 times 20, right? We can assume that there are more than 200 axles in population, right? That's the only way we can use that. And so now we're golden. So what happens, you guys, if you're taking an SRS from any population, right? It doesn't tell you that it's normal. You're totally okay as long as you quote the CLT, okay? If your sample size is bigger than 30, so if your sample greater than or equal to 30, say the CLT guarantees normality. Okay? And really what that's saying, you guys, is what if your population was totally skewed right, heavily skewed right, and you go take a sample of size 100 from that population, you're going to get an approximately normal shape, even if it's heavily skewed. Okay? So this just addresses the normality condition. Okay? I am going to let's see if we can get in here quickly because this video is getting kind of long. So I'll kind of read through this and skip over some things. But you got a bank in a small town based on thousands, right? There's your key, thousands of transactions in the past year. They know that the average money request is 87. So I'm going to write that down. Population average, $87. Standard deviation of the population, $52. Whoa. So that's pretty variable, right? So people take out a lot more than 87, a lot less. Then it says the distribution of money requested is strongly skewed to the right. The bank estimates that there will be 50 customer requests for cash ATM each day. It's trying to decide how much total cash should be stocked in the machine at the beginning of each day. All right, so we want to calculate the probability that a random sample of 50 customers would require a total of 5,000 or more, which is an average request of 100 per customer. So we're trying to find the probability that X bar is greater than 100, right? The only way we can do this is if we have a mean. The mean of your sample is just equal to population mean, which is 87. Your standard deviation of your sample, by definition, is the population standard deviation over the square root of your sample size. So take 52, divide by a square root of 50. And you get 7 I'm just going to round it here to 7.4. Now I've got a mean and a standard deviation. Wouldn't I really like to go down here and hit second distribution? Normal CDF, yes. So how do I know I can do that? Well, there's two things. First, you can't use your standard deviation unless you check, is my population greater than or equal to 10 times 50, 500? I'm going to give it a check mark. This is good for an AP reader. They're good. It says there are thousands of transactions. So yes, I'm okay with the fact that the population sample is bigger than 500. What about normality? Okay, this is the big one. Normality. Did they tell me that the population is approximately normal? No, they did exactly the opposite. They said it's strongly skewed to the right. But you can say, yes, since my sample size greater than or equal to 30, we can assume distribution is approximately normal. Now you're home free, you guys. As soon as you can assume that it's normally distributed, you can go click that normal CDF button. You can say, look, what's the probability that it's greater than 100 to 10,000 with a mean of 87 and a standard deviation of 7.4? You're off to the races. Obviously, you guys would write all that stuff out and you get 0.04. Okay, so there's a 4% chance that the bank doesn't have enough money. And somebody, right, who's making more money than the statistician gets to decide whether they transfer money to the bank to cover that 4% chance, or they're willing to assume that risk at a couple customers that get pretty ticked off at the end of the day and there's no money left in the ATM. Okay, all right, I'm running out of voice. I'm going to skip B for now, but we'll chat again. I haven't decided on whether I'm going to do another lesson on Friday or not. I'll post about that soon. Hope you guys are doing well. Take care.